Hello students, the paper which we are discussing is PhD 4.2 Condensed Matter Physics 3 Special, and we have discussed the syllabus of the unit number 3, that is semiconductor devices. This syllabus can be divided into three parts. The first part is PN junction in equilibrium. The second part is PN junction in non-equilibrium, and the third part is PN devices. Now coming to the first part, that is PN junction in equilibrium. In that we have discussed space charge region and potential diagram of PN junction. In today's lecture, let us discuss the barrier potential. So barrier potential will be the discussion of this lecture. Now let us see what things we have discussed. In space charge region, we have seen the definition of space charge, and next was the potential diagram of PN junction. So we have seen how the PN junction is formed, and after the formation of PN junction, how free electrons and free holes are formed, and how immobile positive and negative ions are formed. So this is the potential diagram of a PN junction. So this is the conduction band on the P side, and this is the valence band on the P side, and here this is the conduction band on the N side, and this is the conduction band on the valence band on the N side. So what happens, that's what we have discussed. Now coming to today's lecture is barrier potential. So the question on this can be, derive an expression for the barrier potential of the PN junction. So that can be the question. So again, for that, consider a PN junction when no external voltage is applied. So we are having a barrier PN junction in a condition that no external voltage is applied. That means for the PN junction, there is no external battery connected here. So we can see here there is no external battery. So consider a PN junction when no external voltage is applied to the junction. So when this happens, then what will happen? No current passes through the external circuit even when P and N regions are shorted as shown below. So if you look at this PN junction, so this is the PN junction. So here this side we have the P type, and here this side we have the N type. So this side it is P type, this side it is N type, and in between this we have the depletion region. And here this A indicates the boundary of the depletion region, and here B also indicates the boundary of the depletion region. Okay, so this is the diagram. So now when there is no external battery connected, so thus the net current through the junction must be zero separately for free electrons and holes. Okay, so here for free electrons and holes. So if we look here, as soon as PN junction is formed, so there will be motion of both electrons and holes. So there will be motion of both electrons and holes. Now, because of electrons motion and holes motion across the p-n junction or across the depletion region, so the current will be formed. So the current because of electrons is the electron current, and the current because of holes is the hole current. So separately for electrons and holes, the net current through the junction must be 0 separately for free electrons and holes. So now in this discussion, now what we will do is we will just consider the current due to electrons. So we are going to consider the current due to electrons only. So this derivation can also be done by considering the whole current, but for simplicity what we will do is we will consider the current due to electrons. So that's why let us consider only the free electron current density. So we are considering only free electron current density but not the whole density. So if we look at the free electron current density, again the free electron current density has got two components. It is having two components. One is electron drift current. One is electron drift current and the other one is electron diffusion current. So these are the two components of the electron current density. So if you look at the diagram, so here the direction of those two components are mentioned here. So if we see here, the electrons which will travel from the n region to the p region, so they constitute the electron diffusion current. So the electron which is moving from p region to n region, the electrons which are moving from n region to p region, they constitute the electron diffusion current. And the electrons which are moving from p region to n region, they constitute electron drift current. Okay, so these are the two components. One is the electron diffusion current and the other one is the electron drift current. Now let us discuss these two currents, these two components one by one. So the first thing is electron drift current. So let us see what is electron drift current. It is due to flow of electrons from p region to n region under the influence of the field on account of the potential barrier. So we should remember, so what is the cause for the electron drift current? It is due to flow of electrons from p region to n region. So we have seen here, so from p region to n region, so this one is electron drift current under the influence of the field on account of the potential barrier. So now this electron drift current is given by Jn is equal to n E mu subscript n and capital E. So this is the expression for electron drift current. So now you may ask the question how this expression is coming. So this is a fundamental electron density expression. So in this expression, which is electron drift current, let us see the terms one by one. So Jn is equal to n e mu n into E. So now E is the electric field intensity due to barrier voltage Vb. Now the barrier voltage let us denote it by Vb. So Vb denotes the barrier voltage. Next, N is the density of free electrons and mu n is the mobility. Mu n is the mobility of the electrons. So these are the things in this expression. Jn is equal to Ne mu n E, where E is electrical field intensity due to barrier voltage, N is density of free electrons, and mu n is mobility. So this is the expression for electron drift current. Now let us see the expression for electron diffusion current. First let us see the cause of electron diffusion current, and if you will go back to the diagram, so here is the electron diffusion current and it is due to flow of electrons from N region to P region. So electron diffusion current it is due to flow of electrons from the N region to P region, where the free electrons are the majority carriers, to the P region where they are minority carriers. That is due to diffusion. So the name itself suggests that it is due to diffusion, electron diffusion current. Now if we go back to the diagram here, so we can see here in the N region there are more electrons compared to the P region. Now the electrons will diffuse from a region of higher concentration to a region of lower concentration. So because of this movement of electrons from a region of higher concentration, that is from N type region, to a region of lower concentration, that is P type region, so such kind of current is called as electron diffusion current. So it is due to flow of electrons from the N region to P region, where the free electrons are the majority carriers, to the P region where they are minority carriers. That is due to diffusion. So now the expression for electron diffusion current is given by this expression, that is Jn prime is equal to E dn dn by dx. So this is the expression for the electron diffusion current. So now we have got two expressions. One is the expression for electron diffusion current, that is Jn dash is equal to E dn dn by dx, and the other expression is Jn is equal to n e mu n e. So this is the expression for electron drift current and this is the expression for electron diffusion current. So in this expression dn is diffusion constant for electron and dn by dx is the gradient of the electron density in the x direction. So this is the expression for electron diffusion current. And now when there is no external current, that is when external current is 0. So if we look at the diagram here, so from this side, from P region, so we can see here, if we look here from this P region, and from here, when we are connecting it from here to here, there is no battery connected here. So from here to here, there is no battery connected. So therefore, when external current is 0, then Jn plus Jn dash will be equal to 0. That is, if we add the electron drift current, which is given by Jn, and the electron diffusion current, that is Jn dash, both should be equal to 0. So when external current is 0. So now what we have to do is, now bring the value of Jn and bring the value of Jn dash and just substitute it in this equation. So the value of Jn is equal to N E mu N E. So which is substituted here. Now the value of Jn dash is E dn by dx, which is substituted here. So now from here onwards, it is just a mathematical steps. I hope at this point you are clear with the concepts of the two components of electron current density. So the one component is electron drift current, and the second component is electron diffusion current. This is the expression for electron drift current, and this is the expression for electron diffusion current. So when the net current is 0, that means both the components, when you add together, so the net density what we get is 0. Now what we have done is, we have substituted the values of Jn and Jn dash here. So from here onwards, it's just a mathematical steps. Now what we will do is, we will take the second term. So we will transfer the second term onto the right hand side. So when we do that, so what we get is, here there will be a negative sign. Now again what we do is, so here we have the negative sign, we will bring it this side, and we have dn by dx, so that will bring it this side. So that will become this negative side also, then next to negative sign also we will take it this side. So on the left hand side we will be having minus e dx. Now on the right hand side, so we will be having dn as it is in its place, and we will take this mu n this side and n also this side. So we transfer it this side, and the thing which we can see here is this e, so this e and this e both get cancelled. So after doing this transformation, we get this equation, minus e dx so this equation is obtained. So minus e dx is equal to dn by mu n into dn by n. Now what we will do is, integrating both sides over the region a to b. Now the question is, why we are integrating it over A to B. So here we are integrating it from A to B. Right? So why we have considered the integration from A to B? The answer is, if you look at the diagram again once again, so these boundaries we have taken it as A and B. So we have denoted by A and B. So there is no compulsion in denoting it by A and B. It can also be denoted by x1, x2 or some other symbols. So as the barrier potential is developed in this depletion region, so we are integrating from A to B. Okay, so integrating both sides over the region A to B. So if we integrate it, so we get this one. So dn and mu n are the constants. So that's why they can be taken outside. So integration of here we have taken, so n subscript n, and here we have taken n subscript p. Okay, so dn by n. So now if we integrate this side, so e dx will get it as dv. So we will get it as dv, and here this side as it is. So let us call this as equation number 1. So this is equation number 1. Now LHS in the above equation, so this LHS in the above equation is due to the fact that electric field is negative potential gradient. So we know that dv by dx is equal to minus E. So that's why, so we get dv here. And now on the RHS, so what are this? N subscript n and n subscript p. So n subscript n, so that is given here. So n subscript n and n subscript p are the electron densities, in the n region and p region. So here, so nn is the electron density in the n region, and n subscript p is the electron density in the p region. So this n, so this n, so this n denotes electron density, this n, and this subscripts, they denote the region. So this denotes the n region and this denotes the p region. So nn and np are the electron densities in the n region and p region. So if we solve this equation number 1, then it becomes, so on this side if we solve this one, so it becomes Va minus Vb is equal to dn upon mu n, and if we integrate this one, so this is integration of 1 by n. So integration of 1 by n will be ln, then if we substitute the limits, then we get ln of n by np. So where, so here we have Va and Vb, where Va and Vb are the potentials at the points A and B respectively, and this potential difference is nothing but barrier potential. So what do we mean by barrier potential? Barrier potential is the potential difference between this point A and point B. So if we denote the potential at A as V A and the potential at B as VB, so the difference Va minus Vb gives this potential in this area, that is the depletion region, that is nothing but our barrier potential. So VA minus VB is nothing but the barrier potential. So VA minus VB is nothing but the barrier potential. So VA minus VB is equal to dN upon mu n ln nn by np, where VA and VB are the potentials at the points A and B respectively, and this potential difference is nothing but the barrier potential. So this is barrier potential. So let us denote the barrier potential by VB. So VB is the barrier potential. So this equation we get. Equation number 2. So just what we have done is VA minus VB is nothing but the barrier potential, and we have denoted the barrier potential with VB. So this is the barrier potential. Now let us play with this equation. So if you look at this equation, so this is not in a good looking form. So let us play with this equation and let us convert it into a more readable form. So here if you look here, so this one dN by mu n. So this dN by mu n, so this is nothing but kBT by E. So these things in detail you will study it in the second unit. So how dN by mu n is equal to kBT by E. So dN by mu n is equal to kBT by E. So we will take this and we will substitute in the equation number 2. So our equation number 2 becomes VB is equal to kBTE. So here instead of dN by mu n, so we have substituted by kBTE and then ln nn by np. So let us call this as equation number 3. So if we rearrange these things, then what we get is, so applying ln on both sides, okay, then doing some mathematical operations, logarithmic operations, then this can be written as nn is equal to np e raised to evb by kbt. So that's equation number 4. So equation number 3 is the barrier. So this equation, we are talking about this equation, equation number 3. So equation number 3 is the barrier potential when electron current is considered. Okay, equation number 3, this equation is the barrier potential when electron current is considered. So here I had discussed that there will be two types of currents. One will be the electron current and another one is hole current. And for the simplicity, what we have done is we have considered just the electron current now, and we have done the derivation. And after considering the electron current, so that was again divided into two components: electron drift current and electron diffusion current. Similarly, if you consider holes, then we will be getting hole drift current and hole diffusion current. So again, no need to do it again once again. So what we obtained, equation number 3, is barrier potential when electron current is considered. Now if we consider the hole current, okay, if we considering the hole current, then we have this expression. So this expression Pn is equal to Ni square divided by N subscript N. Then by using this one, we can show that VB is equal to KBTE ln PPPN. So here, so both the equations are here. So consider these things. So here is one equation. So this is one equation, and here is one more equation. Okay. So look at both the equations. So here VB is equal to KBT by E ln NN by NP. So this is if we consider the electrons. So if you consider the holes, the equation will be like this. So the only difference is that here we are having PP and Pn. Here we are having NN and NP. So I told you that this P indicates the hole current, and here the N indicates the electrons, whereas the subscripts indicate the regions. So this is P region and this is N region. So this is the barrier potential if we consider the electrons. This is the barrier potential if we consider the holes. Now by using this relation, Pn is equal to Ni square by Nn. So this equation can be written in this form. So which will be Vb is equal to Kbt by E ln Pp Nn by Ni square. So this is just a mathematical thing. So we are using this one and we are substituting it in this equation, and then what we get is we get equation number 5. And we also know that, or like how we have written equation number 4, that is by using some mathematical algebra, the logarithmic algebra. In the same way we can write Pp is equal to Pn e to the power of EVB by KBT. So here again we get two more equations. So here equation number 4 is the equation if you consider the electrons, and equation number 6 if you consider the holes. So these are the relations. So barrier potential. Now if you substitute the values for a typical germanium, PN junction with doping of 10 to the power of 22 atoms per cubic meter. So if you consider the values here, then what we get is Vb is 0.3 volts. So these are the various expressions for the barrier potential. So this is the derivation for barrier potential. So the main thing which we have to see is that if you consider the electrons, so what type of currents we will have? We will have two types of currents. One is electron drift current, and this is its expression. Then electron diffusion current, and this is its expression. When net current is 0, then when we add both the things, then it will be 0. Then the mathematical steps. So if we come here, so these are the various expressions for the barrier potential. So the equations which should be remembered in the case of barrier potential are So this equation should be remembered. So equation number 3, this should be remembered, and its counterpart, if we consider the uh, holes, is this one, and if you make some substitution, then we get this equation. And the other one which should be remembered is equation number 4, and its counterpart when we consider the holes is equation number 6. So this is the end of potential barrier. In the next lecture we will go for the barrier